Okay, a 500 turn solenoid has a length of 10 centimeter and cross-sectional area of 10 centimeter square. A coil of 100 turns is wound at the center of the solenoid. Calculate the magnetic flux through the coil if the current of 2 ampere flows in the solenoid and the mutual inductance of the coil and solenoid. Good. So first identify, this is a case about self-induction or mutual induction. To know whether it's self-induction or mutual induction, you must see whether it has only one coil or two coil. If one coil means it's self-induction. If there are two coil involved, then it is mutual induction. Okay, so look at here. It has a solenoid and also a coil. So this is considered like two coil. Okay, two coils. So this is about mutual induction. Okay, mutual induction. Anyway, there's a difference between solenoid and coil. Solenoid normally has current. I can say this one got current. Okay, got initial current. But then coil has no current. Yeah, no current initially. Yeah, solenoid, it initially has current that produce magnetic field, and then coil is the one that receive the magnetic flux from solenoid, and the coil, it has no current initially, but then the induced EMF will happen in the coil. Okay, solenoid is the one that has current initially and has magnetic field, and coil is the one who receive magnetic field or magnetic flux from solenoid. Okay, so like that. Yeah, so here it provides us several information. So this is about mutual induction. Okay, two coils. Okay, so I think it's better we divide this into two columns. Okay, put the information for solenoid under one column, put the information for coil under one column. That's a more systematic way to do it. Yeah, so this is for question A. So we have a solenoid and we have coil. Okay, I can say this one has current initially, this one has no current initially. Yeah, no current initially. So okay, what I can say is solenoid provide magnetic flux. Okay, or we can say provide magnetic field. He provide magnetic field for the coil. Then this coil will induce EMF. Okay, when there is a change, when the current changes. Okay, so when there is a current changes in solenoid, when there is current changes in solenoid, so there will be a change of magnetic flux in the coil, so it will be induced EMF in the coil. Understand? That's how it happens. Yeah, change of, because this is about mutual induction, because there is a changes of current in solenoid, so there will induce EMF in the neighboring coil. Yeah, induce EMF in the neighboring coil. Okay, all right, so let's write down the information we have. We have the 500 turns. Okay, maybe we should label this as number 1, this one as number 2. Okay, so here, this one solenoid, we have N1 is 500 turns, and then length, put this as L1, so this is 10 centimeter, so change to meter is 0.1 meter. Yeah, so 10 centimeter divided by 100, you get 0.1 meter. Yeah, 0.1 meter. And then cross-sectional area of 10 centimeter square. So that's area 1. So just now this one is 10 centimeter. So change to meter, become 0.1 meter. Okay, this one is 10 centimeter square. Okay, 10 centimeter square is it is 10 exponent. Centi is -2. Centi is -2. Square, you get -4. -4. So this is the area. Okay, and then coil has 100 turns. This one is N2. Yeah, N2. So it's 100 turns. Wood at the center of solenoid. Yeah, wood at the center of solenoid. Okay, so what I can say is the setup is like this lah. The setup is like this. We have a solenoid. Okay, initially it has the current, you know. Okay, let me okay, it has the current. Maybe. Okay, let me delete first. Okay, it has the variable resistor here, you know, EMF. It has the battery, so it has the current, you know, it has the current, so it has the magnetic field, you know, it has the magnetic field. Oops, it has the magnetic field. Oops, wow. It has the magnetic field. Okay. So and then there is a coil at the middle. Maybe there's a coil at the middle. Okay. That we have used a galvanometer to see there's the induced current. Okay. So this one is the solenoid, and the middle one is the coil. Okay. The one that has current is the solenoid. It's a solenoid, and the coil is the one who receives the magnetic field or magnetic flux from the solenoid. Yeah. So induced EMF in the coil. Yeah? There will be induced EMF in the coil later on. Okay. Induced EMF, induced current happen in the coil. Induced current happen in the coil. Okay. So all right. Okay. So at the middle. So okay. So where's the magnetic flux through the coil if the current of 2 ampere flows in the solenoid? So 2 ampere is the current in the solenoid. So I can put that as I1 over here. I1, 2 ampere. All right. So I want to find the magnetic flux. So magnetic flux is actually no linkage, isn't it? No linkage. No, the word linkage. So that means it's just a small phi lah. Just a small phi. I want to find the small phi. Not the. It doesn't have the word linkage, right? Doesn't have the word linkage. That means this is magnetic flux through one turn only. This is magnetic flux for one turn only. Magnetic flux for one turn only. Yeah, magnetic flux for one turn only. Not the magnetic flux linkage. Okay, not the magnetic flux linkage. Okay, so let's find out. So I want to find a phi, small phi. So how are you going to do it? Okay, so basically this is the formulas. Yeah, I would like to write down this formula. Copy this first. Okay, so let's see what formula can we use. This one, I put it here. Okay. See. So how are you going to find the magnetic flux for the coil? Magnetic flux from the coil. I have the. Do I have mutual induction? I don't have yet. Mutual inductance. I don't have yet. Mu naught N1 N2 A over L. Okay. Flux for coil. Do I have the current? I have the current. I can use this formula, right? I can use this formula. Okay. Okay. I think we can do the question 2 first. Find the mutual induction first between the coil and solenoid. And then we return to question 1 and we can find the magnetic flux. Yeah, because I think we need the value of magnetic mutual induction first. Yeah. Okay. So the question 2 just now he asked about mutual inductance, which is M. Yeah, M. So I think we do the question 2 first. Okay, before we do question 1, create question 2 first. Mutual inductance we can find. Okay, use these equations. Yeah. All right. We can use these equations. Okay. M equal to mu naught M1 M2 A1 over L1. And find the mutual inductance. All right. So M equal to mu naught N1 N2 A1 over L1. Okay. So N1 N2 A1 over L1. I have everything. Yeah. So okay. So what is the value of mu naught? Mu naught can find from list of constant. Okay, list of constant provided mu naught is permeability constant 4 pi exponent negative 7. So that's the value 4 pi exponent negative 7. Okay, and then N1 is 500 turns, N2 is 100, and then A1 is 10 cm square, or change to meter square. Change to SI unit. So it is 10 exponent negative 4 meter square. Change to SI unit already. Yeah, centimeter square. Change to meter square. And then divided by the length. Length is 10 centimeter. Change to meter, so it's 0.1 meter. Okay, so what's the value of mutual inductance? Okay, so 4 pi exponent negative 7 times 100 500 times 100 times 10 exponent negative 4. Okay, so and then divided by 0.1. So it's 6.28 exponent negative 4 Henry. Mutual inductance is Henry unit. Okay, Henry. Okay, so I got the mutual inductance ready. So I think you can do question 1. Find the magnetic flux. Okay, magnetic flux through the coil. Magnetic flux through the coil. That means I need this is considered as because coil is the number 2, right? Number 2, the one has no current. Okay, the current is in the solenoid, but the current in the solenoid changes. So the magnetic flux that he provide for coil also changes. The magnetic flux he provide for the coil also changes. So there will be induced EMF in this neighboring coil. So okay, this is considered as phi 2. I want to find phi 2. So okay, so want to find phi 2. So what is phi 2? Yeah. So no word linkage means this is a small phi for 1 turn only. Magnetic flux for 1 turn only. Okay. So okay, I can use the formula. I think I can use this formula. Okay, to find the phi 2. Yeah, phi 2. Okay, so it's the current is in I1. Okay, because 2 ampere. I1. MI1 equal to N2 phi 2. Okay, N2 phi 2. So okay, so phi 2 is equal to MI1 over N2 over N2. So okay, so 6.28 exponent negative 4. 6.28 exponent negative 24. Current I1 is 2 ampere. And the number of turns for number 2 is 100. Okay, so what is the magnetic flux for coil 2? Let's calculate. Exponent negative 4 multiply 2 divided by 100. So it is 1.256 exponent negative 5 verbal. That's the magnetic flux. Okay, so am I correct? Yeah, for all the answer, the first question is 1.26 exponent negative 5 verbal. That's correct. Okay, that's correct. Secondly, 6.28 negative 4 Henry. 6.28 negative 4 Henry. That's correct also. Good. So for second questions, now an inductor of self-inductance of 5 millihenry is connected to a direct current source which provides a steady current of 3 ampere. If the current increases at the rate of 15 ampere per second, calculate the induced EMF in the inductor. So, okay, for B, is this self-induction or mutual induction? How to know? See whether it has only one coil or two coil. This one, he said only one inductor. Only one inductor. So this one is considered only one coil. Only one coil. So it's considered self-induction. Okay? Self-induction, yeah, only one coil. Okay, okay, so let's do question B. Yeah, let's do question B. Let's do question B. Question B. Yeah. So it has what value? Yeah. Let's look at the question. So inductance. So that's the self-induction. L 5 millihenry. Milli change to exponent negative 3. Yeah. Milli is exponent negative 3. Henry. And then direct current source which provides a steady current of 3 ampere. So I equal to 3 ampere. And then current increases. I see the word increases. Increases means the changes is positive. Yeah, increases means positive. Yeah. About this I will explain later. Increases at the rate. Rate is means per unit time. Per unit time. Yeah, ampere per second. Okay, so that is di dt. That is di dt. Di dt. So the IDT is positive or negative? Positive because it says increase. Increase means positive. Increase means positive. Positive. At the rate of 15 ampere per second. So you see why the IDT is positive? Why the IDT is positive? Because he say increase. He said the current increases. Okay. If current decreases at the rate, yeah, if current decreases, then if he say the current decreases, if current decreases, then the rate of current is negative. Then it's negative. Understand? It's negative. 15 ampere per second. If the word decrease. Understand? If the word decrease, then if decrease, if say current decrease, then you should put negative 15. Negative 15. But this one current increases. Current increases means the IDT is positive. This is important. So if you say current decrease, don't forget to put a negative sign. Don't forget the negative sign. If current increases, is positive sign. Okay. Alright, so induced EMF in the inductor. So I think we can just use the formula. Want to find induced EMF. Induced EMF means what? Means is induced EMF lah. E induced lah. Okay, E induced. Okay, so I can use this formula, self-induction. I can just use this formula, E equal to negative L di over dt. Yeah. Because I already have L and di dt, right? So induced EMF. So I can use the formula E equal to negative L di dt. Okay, so let's use the formula. E equal to negative L di dt. So L is 5 exponent negative 3 Henry. and then didt is positive. It's positive 15 because it says current increases, so that's why it's positive. But this one, the negative sign here is in the formula. You must have this one you must write this one is must write the negative sign here, a must because this one is in the formula. Because this one is in the formula. Okay. If the formula has a negative sign, you must write the negative sign. You cannot neglect. Yeah, cannot neglect. Okay. All right. Okay. So this one, the negative sign you must write because in the formula has a negative sign. Okay. Don't neglect the negative sign. Don't neglect the negative sign. Okay. So what's the answer? Let's calculate. Yeah. Negative 5 exponent negative 3 multiply 15, so it's negative 0.075. Okay. Vote. Don't forget the unit. Vote. Okay, so that's the answer. Okay, am I right? Yes, that's correct. Yeah. So actually this one should have a negative sign. Yeah, you forget the negative sign. Okay, so induced EMF in the inductor is this answer. Yeah, 7.5 exponent negative 2, so which is 0.075 volt. I'm correct. Yeah, I'm correct. So this value is correct. Okay, so that's all for these questions. I hope you understand. Okay. All right. So that's the answer. Okay. See you again. Bye.